Hello everyone, welcome to section 3.6. What we're going to do is we're going to graph these things called rational functions. So what I'd like us to do first is just recall what we were doing in 3.1 through 3.5. So when we were in section 3.1 through 3.5, what we were doing is we were trying to graph polynomials. And when we are graphing a polynomial, we looked for some key features of the polynomial to help us put the graph together. So I want to kind of make a note here. To graph, we looked for key features. Key features of the polynomial. Okay, so for example, let's say we have a polynomial, let's call it p of x. Let's say our polynomial is negative x to the fourth plus 2x cubed plus a 3x squared minus an 8x plus a 4. Okay, so here's a polynomial. So a few of the things that we were looking for is we want to know what the end behavior of the polynomial was. And what we did is we looked at the leading term. This is the leading term. Okay, the leading term is a negative x to the fourth, so that means it'll have the end behavior of a frowny face parabola. So leading term, this told us information about end behavior. We know that the end behavior should look something like this. Another key piece of information we looked for is we looked for the y-intercept. We could find the y-intercept by looking at the constant term. So this is the constant term. This is the constant term, and what the constant term told us, this told us where the y-intercept was. Notice here that p of 0 is equal to 4. When I plug in 0, it'll always just pop out the constant term, so the constant term will always be the y-intercept. Okay, but we needed more to graph this polynomial. Maybe we would want to factor this polynomial. Let's factor this really quick. Okay, what am I going to do to factor this? We could use the rational roots theorem. Okay, what I'm going to do is, I typically don't like negatives on the leading term. So what I'm going to do is, I'm going to already, just before I do anything, factor out a negative. Okay, you don't have to do this, I want to. So we'll factor out a negative, so I'll get an x to the fourth minus 2x cubed minus a 3x squared plus an 8x minus a 4 when I factor out that negative. Okay, we want to factor this, so I think we have to use the rational roots theorem. So our possible zeros, all possible zeros, well, they'll all come from the constant term, so we could get plus or minus 1, plus or minus 2, plus or minus 4. Okay. Let's check if 1 is a root. And what I'm going to do is I'm just going to look at this polynomial. I'm going to factor this piece. I'm going to leave the negative out front. So a 1, a negative 2, a negative 3, an 8, and a negative 4. Let's see if 1 goes into there. Okay, so we'll drop down the 1. 1 times 1 is 1. 1 plus negative 2 is negative 1. 1 times negative 1 is negative 1. Negative 1 and negative 3 is a negative 4. 1 times negative 4 is negative 4. 8 plus negative 4 is 4. And 1 times 4 is 4. Yes, 4 times negative 4, that's a 0. Okay, well, maybe it has a multiplicity of 2. So let's see if it goes in twice. We'll check again. Okay. We'll bring down that 1. 1 times 1 is 1. 1 and negative 1 is 0. 1 times 0 is 0. 0 plus negative 4 is negative 4. 1 times negative 4 is negative 4. We get out a 0. Yes! It goes in twice. Okay, so I think we're able to factor this polynomial. Let's make sure the camera's down a little bit further. There we go. We're able to factor this polynomial. Okay, let's see what it factors to. Okay, we'll erase a little bit of this here. Okay, so I just need this piece here recorded. So this factored to, I had that negative out front. Okay, we saw that 1 went in there twice, so x minus 1 is a factor with a multiplicity of 2. And I'm left with a x squared minus 4 for my quotient. And this will factor too. So this is a negative x minus 1 squared times an x minus 2 times an x plus 2. And now we have this polynomial factored. And now we can graph it. We have its roots. Okay, so the roots are x equals 1. It has a multiplicity of 2. We have a root x equals 2 that has a multiplicity of 1. And we have x equals negative 2, and that has a multiplicity of 1. Now with all these features, these kind of key features, we're able to sketch this polynomial. Let's sketch a loose sketch. I don't know. Let's do a loose sketch. I need more board space. I don't know. Let's just do a quick little sketch right here. Okay. So what's this thing going to look like? Okay, I know it has a y-intercept of 4, so let's mark a 4 here. So graph goes through here. It has end behavior. And let's just erase some of this here. Do it right here. Okay, so we have a y-intercept of 4. We have x-intercepts at 1. We have an x-intercept at 2. We have an x-intercept at negative 2. Here's our end behavior. And now we have to just figure out whether the graph bounces or if it crosses through these. Now, I can already tell just by these kind of key features I've drawn here about how the graph at least kind of has to go. Specifically, without even looking at the multiplicity of negative 2, I know it has to cross because it has to hit this y-intercept. So it better have an odd multiplicity, which we see it does. But I kind of puzzled my way through that. So it's got to hit here. It's got to cross through this y-intercept. Okay, at 1, it looks like it has a multiplicity of 2, so it's going to bounce, and it better cross through to match up with my end behavior. X equal 2 has a multiplicity of 1. Sweet! So here's a rough sketch of that polynomial. So, P of x. Beautiful. So we took these key features, and we were able to draw a loose sketch of the graph. Now this is exactly what we want to do in the next section when we're talking about rational functions. Okay, so what we're going to be doing when we're talking about rational functions, I'll first define what a rational function is, and then from there what we're going to do is we're going to find the key features of a rational function and then piece together its graph. Okay. Okay, so what is a rational function? Okay, so a rational function, let's get a better marker. A rational function is a function of the form. Okay, so in this case, for a rational function, instead of using p of x, I'll use r of x. So we'll say r of x. So our rational function r of x, what a rational function is it's a polynomial divided by another polynomial. So we're going to have a polynomial, how about p of x, and we're dividing it by another polynomial, q of x. So these are polynomials. So instead of graphing polynomials, what would be the graph if we took two polynomials and divided them? That's what we want to learn. Okay, so just a couple of examples of what polynomials or what rational functions look like. So for an example, here's a couple examples of rational functions. Let's say we have something like 2x squared plus 3x plus 5 all over 5x cubed plus 7x minus 9. This would be an example of a rational function. I'm taking a second degree polynomial and I'm dividing it by a third degree polynomial. We want to be able to graph something like this. Or as another example, we could have a polynomial. I don't know, it could be something like 3x plus 1 all over x squared minus 9. Here we have a first degree polynomial divided by a second degree polynomial. Or Maybe one more example. We could have something like, I don't know, 5 over x minus 2. So here we have a 0th degree polynomial divided by a 1st degree polynomial. These are all examples of rational functions. These are all examples of things that we want to be able to graph. Okay, so when we're graphing things like this, what we want to do is we want to look for the key features of these graphs. So I'm going to go ahead and write up the list of things that we're going to be hunting for these rational functions, and those are the things we'll first look for before we try to put the graph together. Okay, so what are these key features that we're going to always look for when we're trying to piece together the graph of a rational function? Okay, key features. Oh, I can't get a good marker today. Can't get a good marker today. Key features of rational functions. Okay. What I'm going to do is I'm going to make a list of things to hunt for. Okay. List of things to hunt for. So the first thing we're always going to look for, and these are things you usually want to typically look for, not just for rational functions or polynomials, but any type of function that you're graphing. What you're going to be wanting to look for are the x and y intercepts. So we're going to want to look for the x-intercepts. Where does the graph cross the x-axis? And we also want to look for the y-intercepts. Those are the first two things we're always going to want to look for. Okay. Another thing that we're going to want to look for, oftentimes, rational functions have horizontal asymptotes and vertical asymptotes. So we're going to want to look for those. So we're going to want to look for vertical asymptotes. Vertical asymptotes, and I'll explain what these are if you don't already know. Okay, and we're also going to want to look for horizontal asymptotes. Horizontal asymptotes. These are the main things we're going to hunt for first. Now there are two more things I'm going to add to this list. Now these don't always happen in rational functions, but they're things to look out for. So another thing to look out for is we could possibly have these features of a graph that are called holes. Rational functions might have holes in a graph. That's exactly what you think about. There's these little holes in the graph. We'll see examples of these. And we could also have these things. We could have maybe not a vertical asymptote or a horizontal asymptote, a vertical asymptote, horizontal asymptote. We might have slant asymptotes, or sometimes called oblique asymptotes. Oblique asymptotes. Okay, so these are the things we want to look for. Okay, we're going to focus first on the number 1, 2, and 3, x and y intercepts, vertical asymptotes, and horizontal asymptotes, and then we'll look for these features that don't always happen, but ones we want to watch out for, holes and oblique asymptotes. Okay, so what I want to do is I just want to draw a couple kind of maybe what we would call our toolkit rational functions, and then we'll do some transformations of those, and we'll define some vocabulary, or I'll label some of these features on a simple polynomial, or on a simple rational function. Okay. So, let's do some simple examples. Okay, these two functions I'm going to graph you are our toolkit functions, so hopefully many of you are familiar with these functions already. I've noticed in the past that students usually struggle with these type of functions or just understanding what they look like, but they pop up all over the place. And if we just have these down, it's just gonna help you in your math career. Okay, so for an example, let's say I have the graph f of x, which is equal to 1 over x. Okay, this is a rational function. I have a 0th degree polynomial divided by a 1st degree polynomial. Well, let's think about what this graph looks like. Okay, so I just like to make a list of inputs and outputs, okay? So for example, notice that I cannot plug in 0 into this function. I cannot plug in 0. I'd be 1, be dividing by 0. 0 is one of those things that we can't do in math. We cannot divide by 0. So this function is not defined at 0. However, I could plug 1 into this function. Say if I evaluate this function at 1, what would be the output? I'd get 1 divided by 1. I'll get an output of 1. Let's say if I plug in 2, for example, I'm going to have 1 divided by 2. I'm going to get a half. So when I plug in a 2, I get out a half. So here's a half. If I plug in a 3, I'm going to get out a 1/3. And if I plug in a 4, I'm going to get out a 1/4, and so on and so forth. If I plug in 10, I'm going to get 1/10. If I plug in 100, I'm going to get 1/100. So what we should realize is the larger values I plug into this function, the smaller the outputs. I plug in 1, I get out 1. I plug in 2, I get out a half. I plug in 3, I get out a third. I plug in 4, I get out a fourth. And so on and so forth. Now if I plug in, I don't know, pretend this is 100. It's going to be 1/100th. It's going to be really close to the x-axis. Okay. Now what happens when I plug in numbers between 0 and 1, for example? What if I evaluate this function, let's say at 1/2? So that would be 1 divided by 1/2. I'm replacing my x value with 1/2. Well, there's two ways you could think about evaluating this. Well, you could ask ourselves the question, how many times does a half go into a whole? I hope you believe that's 2 times. Or another way to think about this is you're taking the number 1. You can think of 1 as 1/1. So 1/1. And you're dividing it by a half. Remember how we divide fractions? We flip and multiply. So 1 times 1. Move this down a little bit further. So we would have 1 divided by 1 times 2/1. I'm flipping the bottom one and multiplying, and we get out 2. So when I plug in a half, I'm going to get out 2. So if I plug in 1/2, I get out 2. Okay. If I plugged in a third, I hope you believe, if I plugged in a third, okay, how many times does a third go into a whole? I hope you believe 3 times. Or similarly over here, you could think about it just by dividing fractions. Okay, so if I plug in a third, I get out 3. If I plug in a third, I get out 3. If I plug in, here's a third. Here's a third. Okay, if I plug in 1/10, I'm gonna get out 10. If I plug in 1/100th, I'm gonna get out 100. If I plug in 1/1,000,000th, I'm gonna get 1,000,000. This graph is gonna explode as I get closer to 0. This graph is gonna explode as I get closer to infinity. Now, this is what the right side of the graph looks like. But what would the left side look like? Well, now I would just be plugging in negative numbers. So if I plugged in -1, I'm going to get an output of -1. If I plug in -2, I'm going to get an output of -2. So this graph, the graph should look a lot similar to the right-hand side, except over here now the outputs are negative, and that's why it's getting a reflection over the x-axis. So this is what the graph of 1/x looks like. Okay, notice here that this graph, draw here in red, it has 2 asymptotes. Okay, this one right here, we call this a vertical asymptote. It's a value or it's a line that the graph gets arbitrarily close to, but never actually gets there. It's gonna get as close as you want to the y-axis, but it'll never actually touch it. Similarly, we also have these horizontal asymptotes. Horizontal asymptote. So in this case here, the larger values I plug in, the larger values of x I plug in, the closer the graph is getting to 0, or the closer the graph is getting to the x-axis. This is a horizontal asymptote. Okay? There's a way that we could kind of describe this behavior using some of our, arrow notation here. What I could describe the behavior using this vertical asymptote is I could say that as x goes to 0 from the right, That means I'm getting closer to 0. I'm on the positive side. As I'm getting closer to 0 from the right, the output of my function is getting closer to infinity. It's blowing up. Similarly over here, I could say, well, as x goes to 0 from the negative side, from the left, as I'm honing in on 0 from the negative side, the outputs of my function are getting closer to negative infinity. Here I'm describing the vertical asymptote. Okay, similarly for this horizontal asymptote, what could I say here? Well, this horizontal asymptote has to do with what's happening when I'm plugging in large values of x. So I could say as x goes to infinity, what's happening? My function f of x is getting closer to 0, but it's getting closer to 0 from the positive side. Similarly over here, I could say as x is getting closer to negative infinity, the outputs of my function are getting closer to 0, but they're getting closer to 0 from the negative side. So that's some language here. This language here is describing the horizontal asymptote. This language here is describing this vertical asymptote. So this is the graph of 1 over x. Okay, let's go ahead and do another one that we want to think about. Let's do the graph of 1 over x. Sometimes called the reciprocal function. Okay, let's say we have a function. Let's say it's f of x, which is equal to 1 over x squared. Okay, now without kind of doing inputs and outputs, let's just think about what's going to happen when I plug in different values. I wonder if I have a better marker over here. Let's see. I bet this marker is nice and juicy. Had it sitting upside down on my desk. Oh, there we go. There we go, beautiful. Okay. So, now let's think about what's going to happen here. Okay, as I plug in larger values for x, like if I plug in 1, I'm going to get 1 over 1 squared, I'm going to get out 1. I plug in 1, I'm going to get out 1. If I plug in 2 now, I'm going to get 1 over 2 squared, I'm going to get 1 over 4. I'm going to get out a fourth. So again, what we should be realizing is the larger values of x I plug in here, the smaller outputs I'm getting. So when I'm plugging in larger values of x, the outputs are getting smaller. And in a similar way, when I plug in numbers between 0 and 1, like for example, if I plugged in 1/2, I'm going to get 1 over 1/2 squared. So this is 1 over a fourth. How many times does a fourth go into 1? It goes in 4 times. So when I plugged in a half, I get out 4. So the smaller numbers I plug in, or the numbers I plug in that are getting closer to 0, the outputs are getting larger. Okay. So notice here, for this graph, I still have this vertical asymptote, and I still have this horizontal asymptote. So already, at least on the right-hand side, just shape-wise, this looks a lot like 1 over x. Okay, but how is it going to really differ from the graph of 1 over x? Well, notice here I have 1 over x squared. So now, notice when I plug in a negative number, for example, -1, -1 squared is +1. So now when I plug in -1, I get an output of 1. When I plug in -2, I'm going to get an output of 1/4. So this graph, because the denominator here is being squared, is going to look like this. This is the graph of 1 over x squared. It looks like a volcano. It looks like a volcano. Okay, so this is the graph of 1 over x squared. Okay. So if I wanted to use some language here to describe what's going on with this vertical asymptote, we would say, well, as x goes to 0, how about as x goes to 0, 0 from the right, the outputs of my function are getting really large. Okay, I could also say, as x is getting closer to 0 from the left, the outputs are getting closer to negative infinity. I'm sorry, no, positive infinity. As I'm getting closer to 0 from the left, the outputs are getting large. If I wanted to describe what's going on with this horizontal asymptote, I could say, well, as x gets closer to infinity, well, f of x is getting closer to 0 from the positive side. Or I could say as x is going towards negative infinity, we could say that f of x is getting closer to 0 also from the right. So here's our vertical and horizontal asymptotes. Okay, let's do something a little bit more complicated. Okay, so here's 1 over x squared. Let's do one more example. Now, the way I'm actually going to do this example is not a typical way that you would graph these polynomials. But in these simple cases, that we can just actually use polynomial division and our ideas of function transformations to graph some simple rational functions. So, as an example, let's say we have that f of x is equal to, how about 3x plus 7 all over x plus 2. Now, this is not going to be the general way you're actually going to graph these. But what I would like to do is, it turns out for this example, I could write this example as a transformation of one of the two functions we saw in the previous ones. I could actually write this as a transformation of 1 over x. And how am I going to do that? I'm going to go ahead and divide these polynomials. So what I'm going to do here is, notice I'm taking this polynomial and I'm dividing it by x plus 2. Well, this is a situation where I can use synthetic division, so let's go ahead and do polynomial division. Or how about we do synthetic division? Synthetic division, okay. I have a 3 and a 7, and I'm dividing it by x plus 2. Remember, we'll put a negative 2 here. Okay, so we'll drop down the 3. Negative 2 times 3, what is that? Is negative 6. Okay, 7 plus negative 6 is a 1. Okay, so we're finished. So this polynomial is the same thing when I divide it. Well, it's going to be our quotient, the 3, plus I have a 1 all over my x plus 2. Okay, so this is another way to write this. Okay, notice, for this specific example, how about I write this in a different way? How about I write this as 1 over x plus 2 plus 3. I'm just flipping the order of addition. Let's go ahead for fun and put some parentheses right here. Notice that this is a transformation. Right here. This is a transformation. This is a transformation of 1 over x. Well, what have I done to 1 over x? Notice here, maybe in red, notice here that I'm adding 2 to the inputs, so this shifts 1 over x to the left by 2 units. Now notice what else I'm doing. I'm adding 3 to the outside of this function. So this shifts 1 over x up by 3 units. So now what I can do is I can easily graph this. Okay? Well, remember what 1 over x looks like? Remember what 1 over x looks like? We should never forget this graph. We should never forget this graph. So this is what 1 over x looks like. Okay, so what's going to happen here if I'm going to shift this graph, looks like to the left 2 units and up 3 units. Basically, I'm just moving where my asymptotes are. So if I'm going to take this graph and I want to graph this one. Okay, well let's see. I'm going to be moving it to the left 2 units, so 1, 2. Okay, so my vertical asymptote has shifted. And I've also shifted the graph up by 3 units. 1, 2, 3. So now, this is where my new horizontal asymptote will be. Okay, so now I can sketch this graph. graph will look like this. So here's the graph of f of x. Beautiful. Okay, so now just some of the features on the graph that we'll often be looking for. Now, these rational functions won't always have these features, but just to label a few of them. Okay, we have right here, this is our y-intercept. Okay, here, looks like for this specific example, we have one x-intercept. We have one x-intercept. Okay, and then we also have, this will be our horizontal asymptote. And this here will be our vertical asymptote. So what we're going to be doing for most examples, we won't actually be dividing polynomials and seeing things as transformations, because oftentimes the graphs get really complicated. We can only really do this method in very simple examples. But however, what we're going to be hunting for when we're graphing these is we want to know where the horizontal asymptote is, the vertical asymptote is. If I know where the graph crosses the y-axis, if I know where it crosses the x-axis, then I'm going to have the ability to piece the graph together when they get really complicated. We'll start doing those in the next video. Okay, take care. We'll see you then.